We did in class a fairly careful experiment dropping coffee filters. The procedure was to drop a coffee filter with at least one other coffee filter. Actually, we dropped, 2m here represents twice the mass of a coffee filter. M here represents the mass of a coffee filter. And you see we dropped a triple mass, that's 3 coffee filters in one, against a mass of 1, and 4 times the mass against the mass of a coffee filter. And I don't think I put the M on this one. Now, we assume in each case that the single coffee filter, which is dropped from lower and lower heights, in order to hit the ground at the same time or hit the floor at the same time that the heavier coffee filter does, we assume that this coffee filter always travels downward at the same terminal velocity, and that terminal velocity is attained very early, so that the average velocity is pretty close to the terminal velocity. Okay, so our basic assumption, and this isn't completely correct because it takes a little while to get to terminal velocity, but the basic assumption is that the average velocity of the drop is equal to the terminal velocity. Now, we observed that when we had a doubled mass dropped at the same time as a single mass, the doubled mass dropped from 200 centimeters. They would hit simultaneously when the single mass was dropped from about 128 centimeters. And we double checked that. Sometimes the filters spread out a little bit, so that maybe one filter is wider than the other. So we took the extra mass and we switched filters. We put the extra mass in this filter and then dropped this single filter from here. And the results were always very consistent. So we tried to control for the fact that the surface area of the cylinder seems to change as the cylinders get old. In any case, we observed that when a doubled mass was dropped from 200 centimeters, we dropped the single mass from 128 centimeters, and they hit simultaneously. For the tripled mass, we had to drop the single mass from 92 centimeters closer to the ground, because of course this is going to fall closer, and then they would hit simultaneously. And for 4 times the mass, a 77 centimeter drop caused them to hit simultaneously. Now, what do we conclude from this? You recall that we've talked about the idea that the force of air resistance on any falling object at terminal velocity is equal to its weight. So we're going to compare the force of air resistance to what we assume is the terminal velocity of each of these weights. Now, to get the terminal velocity of each weight, well, we're going to use V2m for the velocity when we had twice the mass. So V2m is going to be in proportion to the terminal velocity of the single mass. It's going to be in the same proportion as these heights, but actually it's going to be an inverse proportion to these heights. That is, obviously the larger mass is moving faster than the smaller mass, so that V2m is going to be greater than V, and really that should read V1, which is the velocity of a single coffee filter. And the proportionality is going to be 200, or the proportion is going to be 200 to 128, or about 1.6, so that the velocity observed, at least the average velocity of the doubled mass, seems to be about 1.6 times the velocity of the single mass. And if we assume that both masses are moving always at their terminal velocity, then the terminal velocity here is going to be 1.6 times this. Similarly, over here we're going to conclude that the terminal velocity of the tripled mass is 290 seconds of the velocity of the single mass, or 2.2 times the velocity of the single mass, and that the terminal velocity of the quadrupled mass, the 4 times the mass, is going to be 2.6 times the velocity of the single mass. Let's put a 1 on that V there.